Welcome to this video. We are about to have a look how to make code that will run ultra fast, a code that is easy to be developed. And this code is about single precision floating point computing. Technologies that will be used for this are Lazarus, FreePascal, AVX and AVX2. Everything here is in regards to the uvolume unit that belongs to the conscious artificial intelligence project. This video is pretty much hands-on, and we are about to start from the beginning. Here I have an empty project, Lazarus project. I'll show you some of the project options so far. What I have is pretty much default release and debug settings. I will leave for release for now. We can change later if required. So everything here relates to a unit called uvolume. The name of the unit, why this is called volume, because this unit allows you to create up to 3-dimensional vectors. For our presentation we use probably just only one dimension, but it is possible to use up to 3. Here we have some defines that we can use later for comparing plain Pascal code and then Pascal with directly AVX code. We have AVX for both 32 and 64 machines. So let's start first for our testing, speed testing. First I will place a button here just for us to be able to launch the calculation. Get time. And then I need a place here where I will have my result. This presentation is not about application design, so whatever I place here is good enough. I'll just change the name. Okay, and we are ready to start. So what I need here, I need something where I can record the actual time. So what I will do, I'll create 2 variables here so we can record time. I need as well the volume objects that will be used for floating point calculation. The class we are about to use is called tNetVolume. The Conscious Artificial Intelligence project is about artificial intelligence. This is a class usually used with when developing applications for artificial intelligence. So why we have this name goes beyond the scope of this presentation. So here we have a create method, and I'll create with only one dimension I'll create D2 exactly the same. In the end I'll free these both, T1 free. Okay, so I will fill, to make things easier, I will fill the first vector with number 1, and I'll fill the second one with number 2. For our experiment and speed calculation, we'll do dot products. Dot products are very common in artificial intelligence. Okay, we need to gather the time. So here we get the start time. And the total time. Okay, we just need to transform this let's see, lamp result float. Okay, that should be enough. I'll just run to check what happens. Here we go, we have the application running. Get time 0, that makes sense. This is not doing anything yet. Plus seconds. That should be good. Okay. So we have two vectors with 100 elements each. So here I'll put my code. This code is the code that will actually do the dot product. So I need a counter for the looping. That will be integer. And I will run this. Let me think. I think I will run our test 20 billion times. For CNT from 1 to 20, 1, 2, 3, 1, 2, 3, 20 million. Boom, begin, end. So here we go. Actually, we'll create one more vector. Why? Let me think. No, that's good. Dot product result single. So T1, this class, the net volume, has plenty methods here that we can use. I'm interested in dot product. Dot product T2. Just for us to check if the result is the result we are expecting. The dot product, in the dot product we multiply each element with the equivalent element in the other array, and then we make a sum. So given we have 100 elements and 1 times 2 on each position of the array, so I am expecting a result of 200, just for us to know if this is being properly calculated. I will throw actually we'll do something better. I'll create 2 labels, one for the result and one for the time. So lab result and lab time. Okay, so lab time equals string total time and here we'll place the result. Let's see how it goes. I've done something wrong. I missed this. We go again. Here we go. The result is 200, so the result of the dot product is correct. And running 20 million times this dot product is taking almost 7 seconds, running in only 1 core of this machine, the machine I'm using for this presentation. The first thing I would like to show you is at this moment uvolume is using only plain Pascal code. I'll show you. I'll control click the dot product and then I can show you here. This is plain Pascal code. There is nothing special here. There is no AVX, AVX2, just pure Pascal. To give you an idea about the impact of debugging on the speed, I'll come here, project options. So I'll switch from release to debug, and now I'm enabling all error checking plus debugging, and there are some other defines that will not run as a consequence of this. I will show you. So here we have a bunch of inlines that will only be included in the release version, but I have just switched to debug. So we'll have a look now the impact on performance without changing the source code, just switching from release to debug. We'll see. So, and I will actually take notes of our previous results. So pure Pascal code takes 6.8 seconds. 6.8 pure Pascal. Now let's see, and using release settings. Let's see how much will take with pure Pascal, 6.8 seconds, with debug I'll take out while to run. Let's see. $6.8. Let's see if I did anything wrong. Okay, I think I know why we see no difference. Let's see. Okay, we have inline on, macro on. I didn't enable debug. Okay, we'll run again. Okay. Project options. I need to get a path. Okay, that should do the job. Let's try again. $20 million times dot product. It's running. $18 seconds, 18.8. So that's the difference just for enabling debugging settings. So what I will do now, we'll now check the difference from pure Pascal portable code. That's the good thing using pure Pascal, because it's portable. We will switch on the AVX flag. So now we'll see how much you can gain by using uvolume unit. Let's see. We are back to release. And now we will enable. You are looking at Ubuntu 64 machine. So I'm enabling AVX 64 bits. I'll show you what this does to the code. Run build. Okay, I'll control click dot product so you can see the difference. Dot product. We are now in a new portion of the code. If the size is bigger than the minimum size, let's see what is the minimum size. Is 16. Let's see how the dot product is implemented, and is implemented using, as you can see here, registers YMM. They are AVX 32 registers, and we'll see a dot product. We'll check the difference, how much faster is running dot products using AVX code, calling via uvolume unit. Here we go. 0.4 seconds. 0.4 seconds. So now you start to feel the difference. How much faster? 0.44 seconds. AVX uvolume unit release settings. Now what we will do, as you can see, AVX2 here is commented. We're currently using the plain AVX code. So let's see if in this machine we have any gain. From previous experimentation, I couldn't notice any difference, but each machine, each processor has its own architecture. So just because in my machine we are not seeing a lot of difference, that doesn't mean it doesn't make a difference. I believe that this testing machine that you are looking at is bottlenecking memory, and this is a memory intensive operation. Let's test again. So now we are running AVX2. I'll build again. Build. Let's see. 0.44. So not much difference in this machine. You should not take for granted the speed difference from one machine to the other. But as you can see here, the difference is impressive. To have an idea how many gigaflops we are getting, let me see if I can make this calculator. So I'm running this dot product 20 million times. The vector size is 100 that I am using here. And the dot product requires, as you can see here, for each element in the array, it requires 2 floating point operations. I will show you the implementation. It requires 2 operations for each element, a multiplication and an addition here. So there are 2 operations. So 100 elements in the array, it means 200 operations times 20 million. So times 200. And then to get the number of gigaflops, I'll divide by 0.44. 0.44. So let's see how big is this number. We are getting 9 gigaflops. 9 gigaflops in only one core on this machine. So imagine if you have a Xeon Phi or any other machine that has a very high number of cores, AVX enabled. The clock speed of this machine is also not very high. Let's see if I can check the clock speed here. Not sure if I will be able this way. easier way, I think. Let's see. System settings. Let's see if I can get through here. 1.8 gigahertz is my CPU. So considering we are getting 9 gigaflops, it's a lot. You can see that you can really push uvolume really hard. I'll make, before we finish this presentation, I'll make just one more experiment. We'll make 10 times bigger the vector and check if the amount of time also grows 10 times, or we'll find out if uvolume increases in performance for bigger vectors or decreases. We'll find out. So rebuild this experiment. 1000 vector size. Build. Run again. We'll get our timing. Running. 2.776. So evidently this is smaller than 10 times 4 seconds. And it is clear that it becomes more efficient with bigger arrays. 2.7 AVX2 uvolume. And also becomes clear that here we were getting 9 gigaflops. It is clear this is well above 9 gigaflops. Although via settings, I'm not using the fastest processor. So that's very interesting. Okay, I hope you have enjoyed the video. As you can see, you can make calculations way more than 10 times faster using uvolume than using plain Pascal code. I'll just give you an idea what is available in uvolume. You can add vectors, you can subtract vectors, you can multiply, divide, you can copy one from another. You have other options, but the basic things that you always need, that is adding, subtracting, multiplying, and adding, that's useful. It is very common when you are doing linear algebra. You first multiply and then you add, and that's actually very fast. It was implemented also using actually, I'm lying to you. That's plain Pascal. Anyway, I hope you enjoyed the video. I hope you are finishing this video expecting to run your own code with single precision a lot faster than before. And see you next time. I hope you enjoyed.